Okay, now we're going to use smarter notation to take care of everything that we've got written here. But for that, we need to make some introductory remarks about some objects that you'll need to know how to use. Okay, so maybe let's give a new page to this. So this is going to be the section on the field tensor. Okay, so we've already seen the idea of a 4-vector. So how does that go? If a 4-vector transforms, the only thing that you do is that you apply the Lorentz transformation to it. Okay. Now this matrix we've talked about it. It's the thing applying the actual Lorentz transformation. Of course, that takes different forms depending on which particular transformation you're doing. The simplest one is for motion along x at velocity v. Then what we have is that this lambda is just the following 4x4 matrix: gamma minus gamma beta, then 0, 0, minus gamma beta, gamma 0, 0, and then just diagonal 1, 0, 0, 0, 0, 1. Okay, so that's one case where motion is along the x-axis. Right, so that's the way these 4 vectors transform. Now we can think of other objects that have multiple indices. Okay, so an object like a 4-vector is known as a rank 1 tensor. Okay, so 4-vector, vector, it has rank 1 as a tensor. If I had a rank 2 tensor, I would have 2 indices. So I would think of an object that, say, tensor mu, mu. Okay? And now the fun thing is the transformation law. So transfer law. I would write the t bar with indices mu, nu as the transformed t from the original frame. But now I just need to apply 2 of these Lorentz matrices. So mu, call it lambda, and then big lambda mu sigma, and then t would carry indices lambda sigma. And of course, once again, I'm using the Einstein summation convention, so any repeated index is summed over. So on one side of the equation, I mean, right? So the lambda here is summed over, the sigma is also summed over. Now you can view such a tensor again as a 4x4 object, right? So if you want to, you can write it in components, yeah. So t0, 0, t0, 1, t0, 2, t0, 3, etc. Right? t1, 0, t1, 1, t1, 2, t1, 3. Okay, and you can carry on like that, amusing yourself. Okay, t30, t31, 1, yes, t32, t33. Okay, so these are the indices as you would put them, a bit like you would do indices of a matrix. There are some important cases. So if you have a symmetric tensor, then t mu nu is equal to t nu mu. Okay, so it would have 10 possible components. And you can have an anti-symmetric tensor, which states that t mu nu is equal to minus t nu mu. Okay, and maybe we give them subindices, symmetric and anti-symmetric, like this. Okay, so for an anti-symmetric tensor, for some reason that you'll understand very briefly, we'll be quite interested in these anti-symmetric tensor. Okay, anti-sim tensor of rank 2. Well, I would write in the following way. So I would have a T mu nu, and this would be anti-symmetric. So what happens first? Well, the diagonal elements all have to vanish. Okay, 0, 0, 0, 0. And now, of course, I can have non-zero components here. T01, T02, T03. T12, T13, and T23. Sorry, maybe this is not properly lined up here. Let me just redo the alignment a bit. T23 and then 0. But then the other components are fully determined by these 6 ones, right? Because this would have to be minus T01, minus T02, minus T12, minus T03, minus T13, and minus T23. Okay, so it has 6 independent elements. 6 indep elements. Okay, now let's just play with this antisymmetric tensor. So, so under the Lorentz transformation that we had above, yeah. What do we have? Well, we have that we can compute the new components of the antisymmetric tensor, and we have six of them to compute. So let's do one of them for fun. So let's do t bar 0, 1. So what are our rules for this? Well, it would be lambda 0, and now summation index. I can do what I want, so I'll choose mu. Lambda 1 nu, t mu nu. Okay, but now I want to look at which values of mu and nu I can have. So for the 0, in the original thing, I only have the first 2 entries here. Same thing for the 1. Okay, and then for the 2 and 3, it's only the diagonal that works out. So this contains 4 terms. I can do lambda 0, 0, lambda 1, 0, say, t 0, 0, plus lambda 0, 1, lambda again 1, 0, t 1, 0, plus lambda 0, 0, lambda 1, 1, t 0, 1, plus lambda 0, 1, lambda 1, 1, t 1, 1. Okay, but yeah, let's have fun. So t 0, 0 for an antisymmetric tensor is 0. Okay, maybe I should just specify that it's an antisymmetric tensor. Okay, the same thing for t1, 1. This is also 0. And if I look at the value of these leftover elements, lambda 0, 0 is just gamma. The diagonal ones are gamma. And this one, well, sorry, I'm computing the one that's 0. That's not very smart. Let's do this one then. So it's minus gamma beta squared. So gamma squared beta squared. Right? And then this one here is just gamma squared. So t 1, 0 plus gamma squared t 0, 1. But we know that t1, 0 is minus t 0, 1. Okay, so this is t 0, 1 times, I've got a gamma squared, now minus gamma squared beta squared. Okay, but actually this is quite simple, right? Because t 0, 1 gamma squared times 1 minus beta squared. But you see these go away against each other. And this is just t 0, 1. So that's our first component. Okay? So this one transforms quite simply. Then we can do the other one. So let's do the other non-zero. It's not too long. T02. So again, this is what we had: 0 mu 2 nu t mu nu. Okay, but now it's quite simple because there are just two terms. Because for this case, there's only nu is equal to 2, right? So I have lambda 0 0, and then lambda 2 2 is just 1, right? You remember here, just 1. So there's no factor there. So this is just lambda 0 0 times t02 plus lambda 0 1, again 2 2 t. Now I've chosen 1 2. Okay. So again, just substituting the values. This is gamma. This is minus gamma beta. So I've just got gamma times t 02 minus beta t 1 2. Okay, and then I can do the same with the 03. This is very similar. So you see the only difference is in the index 3. So I can already write this as gamma T03 minus beta T13. Okay. Then we can do T bar 1 2, the next non-vanishing element. So now I've got lambda 1 mu, lambda 2 nu, t mu nu. Okay, so this is very similar. So the index mu can take values 0 or 1. Nu will have to be 2. So that would be lambda 1 0 times t 0 2 plus lambda 1 1 t 1 2. Okay, and again substituting. Lambda 1 1 is gamma. This is minus gamma beta. So this is going to be gamma times t 1 2 minus beta t 0 2. Okay, and might as well do them. I mean, see, it's not too complicated. T bar 1 3 again is very similar to this one. I can just do precisely the same thing. So this is just gamma T13 minus beta T03. Okay, and finally the T bar 2 3. You see, this is quite simple, right? Because it's just like the unit matrix working in that space. So that that is straightforwardly equal to T23. Nothing happening there. Okay, so so these are our transformation rules. Now let's observe this thing here. I've got something minus beta something else. Now, if I look at the expressions that we had here, it looks dangerously familiar, right? So if I chose the T01 to be proportional to EX, then this would work well. Then you see the T's on the 0 here, these ones here, if I choose them proportional to the electric field, then it's going to work out well because they have the right transformation law. So this would be the transformation law for EX, and here would be for EY and EZ. Okay. So you see when we look at these equations, we can start doing some identification. So T01 would be proportional to EX, 02 EY, 03 EZ. Okay. And that way we would get our thing. Now there's a little factor of 1 over c squared here and v here, okay, and you can easily convince yourself that there's a very nice little tensor we can write. So comparing with earlier results, for the transformation of EB fields, we can define what's called the electromagnetic field tensor the famous F mu nu, okay, in the following way. It's an antisymmetric rank 2 tensor, okay, with in the spatial part, sorry, in the zero component, just proportional to the electric field. And then it's antisymmetric, so this element would be just minus EX over C, 0. And then in the other components, you have to make an identification. So here there would be BZ minus BY and BX. Okay, and then 0. So these would be the 4 components. And then antisymmetric minus EY over C minus EZ over C, and then minus BZ, BY, and minus BX. Okay, so the point of this notation here is that the Lorentz transformation is simply this one. The F bar mu nu is just twice the application of the Lorentz matrix onto this. Okay? It's as simple as this. So with this proper choice of combination of the elements and arrangement of the elements inside the tensor, the Lorentz transformations become as simple as doing these sums here. There's another nice tensor that also works, that gives you precisely the same transformation laws. It's called G mu nu, nothing to do with general relativity. But in this one, the roles of the, so it's F mu nu, but where you've put E over C into B, and conversely, B into minus E over C. Okay? Yeah, so so you just get some substitution. So I mean, you can write it down. So 0, bx, by, bz, and I'll just write the non-zero components. So minus ez over c, ey over c, and minus ex over c. Okay. And these elements are just the antisymmetric ones. Okay, so these are handy notations that we'll be using at the end to really write some very, very shorthand notations for everything that we've done until now.